Welcome to the Digital System Design Project presentation. It is a complete design journey from specification to implementation, offering a comprehensive approach to digital system development. Here is an overview of the project. The objectives are to design a complete digital system, following industry-standard methodologies and best practices for real-world applications. The scope includes end-to-end development, covering specification analysis, design, implementation, testing, and optimization phases. Let's take a look at the design flow. Step 1 is specification, involving requirements analysis and system definition. Step 2 is design, which includes architecture and logic design. Finally, Step 3 is implementation, focusing on hardware realization and testing. Specification analysis involves two important things: requirements and constraints. Requirements includes functional specifications, performance requirements, interface definitions, and power constraints. Constraints includes area, timing, power budgets, and technology limitations that guide design decisions. Now let us discuss the system architecture. It comprises three modules. First, the input module, which handles data acquisition and pre-processing. Second, the processing core, the heart of the system, which does main computational logic and control. Third, the output module, which formats the results and presents the final interface. Logic design uses methods like Boolean algebra, state machines, and a hierarchical design approach for complex systems. Here's a high-definition language or HDL example code for a counter module. The module takes clock and reset as inputs, and outputs a 4-bit count. Inside the always block, if reset is asserted, count is initialized to 0. Otherwise, count is increment by 1 on every positive edge of the clock. There are generally three implementation strategies. First, Field Programmable Gate Array, or FPGA, which allows for rapid prototyping and flexible reconfiguration during development. Second, Application-Specific Integrated Circuit, or ASIC, which is used for high performance and power efficiency in production. Third, a hybrid approach, which is a combined approach for optimal cost-performance balance. Testing and verification involves several levels of testing. First, unit testing. Second, integration testing. Third, system testing. And fourth, hardware validation. Verification uses formal methods, simulation, and coverage analysis to ensure correctness and reliability. There are 4 optimization techniques. The first is area optimization, which involves resource sharing and logic minimization for compact design. The second is speed optimization, using pipelining and parallel processing for high performance. The third is power optimization, which employs clock gating and voltage scaling for energy efficiency. The fourth is the trade-offs involved in balancing competing requirements for an optimal solution. In conclusion, the key achievements of this project includes a complete system specification, functional design implementation, successful verification, and performance optimization. Future enhancements could include advanced features, scalability improvements, and the integration of emerging technologies. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.